Hello all, welcome to my channel. I'm back with another video. In this video, we will be talking about geospatial analysis. Uh, the reason I'm doing this series is I've been engaged with in a project where we are trying to build a product which deals with geospatial data, and hence I thought of documenting what I am learning and how this is different than other analysis that we do with tabular data. So let's get started. So first thing first, what is geospatial data? So geospatial data basically is an information or is a data that refers to the set of data which describes a geographic location and its characteristics feature. For example, let's say latitude and longitude is a type of geospatial data. Then we have weather data like temperature, sensitivity, humidity, precipitation, fuel index. These are again certain data attributes of a location. It can be of a boundary of area, or it can be a latitude, longitude, or it can be a area of interest that we want to know these attributes. So these types of data is called geospatial data, and the analytics that we do on top of it is called spatial analytics. And spatial analytics allows us to solve complex location-based problems and gain insights into the occurrences by deciphering the patterns that is there in that geographic location. For example, let's say if we are doing an urban planning, we want to know what is the traffic pattern, what is the future water consumption level, future flooding scenarios, what is the terrain, how the houses should be built, what is the soil nature if we are doing farming, what is the chances of a wildfire happening if we are living in a forest area, what is the chances of an overhead wire causing fire or causing damage. Again, that's transmission lines. What is the area in which we should place a cell tower so that we get a larger coverage or most of the coverage of the people who are residing in the area. So these kind of things, these kind of questions can be answered if we do merge the traditional data with the geospatial data, and then combined analytics will provide us these solutions. For example, let's say there are companies which are doing promotions for restaurants, or there are companies which are doing logistics work for retail companies or e-commerce websites to strategically target certain customers in certain geographic areas, or uh, replacement of a cell store location. For example, let's say if we want to know that in which area we should be placing an showroom for a company that attracts most number of eyeballs, or let's say where should be placed an advertising board which will give us maximum number of eyeballs. So that kind of analysis is done with geospatial data. Uh, so in broader terms, we can represent the geospatial data in two ways. One is vector, another one is a raster. Vector is something something similar to like a point or a line or a polygon that represents the geometry of real world entities. It does it in a planar surface, and it is geometric in a sense that it represents uh, uh, area. I mean, it represents shapes as well, and there are different file formats which can represent or which can store vector data like GeoJSON, GeoParquet, WKT, which is well-known text, WKB, well-known binaries, shape files, geo databases. So there are different formats in which vector data can be stored, and there are certain tools which are specifically designed to work with vector data. For example, GDAL, Shapely, GeoPandas. These are well These are tools created specifically to work with vector data. And there are other frameworks like H3 indexing framework or Mosaic framework from Databricks, or a Sedona, which works with both raster as well as vector data, raster frames. So these are the frameworks which we can use to work on with vector data type. Then we have raster data, which is uh, grids, tiles that are arranged in a fashion to represent a region. This is called raster data. We can have raster data. We can think of a raster data as an geography kind of, which has elevation, which has certain other attributes, like we can store uh, for a particular grid, or let's say for particular area, we want to store its different dimensions of the geographic nature of that particular place. So raster comes in handy, and it represents a region. It uh, formats for this type are, for example, geotiff, uh, cloud optimized geotiff, MRF, CRF, ECW. So these are different file formats, or I will say representations that we use to work with raster data. There are certain tools that we can use to work with raster is GDAL, Raster.io, PySed. There are other frameworks as well, similar to as we mentioned in for vector data, Mosaic, Sodeno, and raster frames can be used to work with raster data. So in a sense, if we have to do a difference kind of analysis, like what is vector and what is raster. So in terms of different aspects, the vector data is something which represents a discrete geometric object, while raster data represents a grid of regularly spaced cells, pixels in this case. The precision of a vector data is very high. Raster data has a concept of resolution. So higher the resolution, the lesser the accuracy. Oh, sorry, the lesser the resolution, the higher the accuracy. And so there is a some gap between the accuracy of the precision of vector versus raster. And storage, vector data, because it is not stacked, so it requires more space. Raster data is suitable because it has a representation which requires lesser space. So for a larger data sets, generally raster data is preferred. We can think raster as of a snapshot overlaid up on top of each other as well at a different resolutions or zoom levels. Then we have different file formats, as we discussed, like vector can be represented with zip files or GeoJSON. In case of rasters, we have geotiff, netcat, or image types. So this is about like what is geospatial data, why the analysis is needed, what are different types of geospatial data like vector and rasters. Then comes the geospatial data indexing. So indexing is something which is very important because that allows us to quickly find data in any system. So for example, in normal databases, we have B-tree indexes. We have other kind of indexes as well, but most common one is B-tree. Similar to that, we want spatial data because it is not a numeric or not a string kind of data. Um, it has dimensions which basically we are projecting a 3D object onto a 2D scenario. So the indexing works in differently here. So we have different options of doing indexing in spatial data. So for example, we can have H3, which is Uber's indexing technique. Then we have geo hashes, which has been there since long. And then we have Google's S2, which is again and indexing strategy that divides the whole world in terms of a cube projection, and the projection that they do based on the cubes are into not exactly a rectangular shape, but we can think of a quad angle, like it has four sides. So that kind of shape, and we use that as an indexing mechanism. So let's see how these indexing mechanisms are different. In GeoHash, what we do is we have rectangular cells. Then we use Z order. So if you are if you have seen my earlier videos on Spark, you might have, or Spark or Databricks, you might have understood about Z order and Hilbert curve. So you can, if you haven't done that, you can go and watch that video to understand what a Z order is. So basically, in a quick summary, if I say, so Z order is a way to store data so that similar type of data are stored together. So that's what Z order does. And so GeoHash uses regular cells, which can be square or which can be a rectangle, and they use Z order for space filling. Uh, so what it does, it preserves the spatial hierarchy. Hierarchy in a sense, like each cell will have a parent, and that cell will be completely within that parent itself. So how it will work is, at let's say if we have a bigger square that we divide it, let's say in four different subsections, so each subsection can further be divided into four and four and four recursively. And then, so that's what the each cell is completely within the its parent cell. So that's what this does. It is very simple, it is very fast, and it works very well. It is battle tested, it has been in uses in this industry for long. And but that there were some challenges with this because the shapes were not perfectly aligned. So Google created a new indexing mechanism. So what they did is, they, instead of using the Jador curve, which has challenges because when you move from one layer level to another level, there is a slight boundary where we have scope of overlap. So the same cell being part of two different uh, domains. In case of S2, that is removed because in rather than using a Z order curve, it uses a Hilbert curve where the every rotation is a 90-degree clockwise or anti-clockwise rotation. So that way, the space filling that happens is very efficient. And then it also preserves the spatial hierarchy, like Geo has. Every child is completely within the its parent. And then it uses the projection. What it does, it treats the whole world as an a whole earth as an combination of cubes, and then they project the cube, which is in 3D object, to a 2D plane to make these things work, and then the index is created. Then we have Uber's H3. So Uber wanted to create to map the whole traffic pattern and their driver and uh, riders locations available, and they wanted to have right mapping. Let's say if a cab is at a place A and there are n number of people who are requesting rides, which rider and the ride should be mapped to, the driver and the rider should be mapped to. So they created an indexing strategy which is called H3, which divided the whole earth in terms of many bigger hexagons and some pentagons as well. So the whole structure, the whole earth is now kind of similar to how a football, and it's the older football, earlier days football used to have, like they had also hexagonal shapes, and in between some uh, pentagons were also there. So that is the same structure is used in creating that H3's indexing mechanism. And what it does, it uh, the benefit of using an hexagonal cell is that it is equidistant from all the cells, neighboring cells, and also it's the space filling is very compact. So this was created, so we can use this H3 method to actually create a unified fields as well. For example, let's say if we have geography data, means like say we have vector data as well as we have uh, raster data. So in this case, we have both GeoTIFF for NetCDF as well as SAFE file and GeoDB data. So this one is from coming from vector data. This is coming from raster data, and we want to join this or unify them. So how we can do it? Let's say both of them contains latitude and longitude. So what we can do is we can create H3 index on both of these, where each of the lat and longs will fall in a particular H3 cell, and then we join those two data sets based on that H3 cells itself. We can create the buffers and everything as well. And that way we will be able to map or project the shape file on the raster file or vice versa. And that way we will have both tabular as well as spatial feature in the same place. For example, let's say the save file can be a area of interest, or let's say point of interest, and that is mapped to the raster file, so that instead of reading the whole raster file, we are only reading the subset of raster file, so that we can do the analysis on top of that, which is very unique way of combining data. So these are some indexing strategies which are there for the spatial data. There are others as well, which is A5 pentagon or Bing's quad key option is also there. Once we have this spatial indexes covered, we also have a concept of spatial. There are some other terms as well, like spatial partitioning. So how we partition this data, like similar to how we will partition, let's say, a tabular data into, for example, if you're coming from Spark, you might have seen data frames that which are each partition of the data frame is sitting on a different node, and then there is a logical abstraction on top of it. So when we talk to that, we talk to a single, instead of talking to multiple nodes, we talk to a single node which is distributing the work and everything. So same concept is there in Spark, sorry, in spatial databases as well. We can do space partitioning based on quad tree or KD tree algorithms, and we have concept of space filling that we have already discussed, like Z order and Hilbert curve. So that allows us to compactly fill the data. And then we have this space grid indexing, which is Geo has S2 and S3. So this is how the data is organized and that kept. Then we have the concept of spatial SQL. So now let's say we have already got the understanding what spatial data is, how it is stored, how we can do indexing and stuff like that. Now how we can run queries on top of it. So that's where this spatial SQL comes. So there are many engines, each of them have their own implementations, but there is a common basic similar way that we have for relational data. Like there are multiple engines, each engines implement the SQL in a different dialect or different format, but the basic things remains common, like join, projection, filtering. So the same way we have a spatial SQL, which is an extension of SQL to work with the spatial data. And some of the common operations that we have is, let's say we want to compare two things, like whether a point is uh, equal to another point or not, whether a line string is equal to another line string or not, whether a polygon is equal to or not equal to some other polygon. Or we can have intersection, saying that okay, whether the two objects or two shapes, whether they intersect with each other or not. We have disjoint, we have within or contains, to find out whether one POI completely engulfs another POI or not. Then we have overlap to see how much is the overlap, or it's completely overlap, or it's a partial overlap, that kind of things, like polygon to polygon overlap we can check. We can have cross as well, that see whether the one multi-point object crosses the other polygon that is there, or multi-polygon that is there. Then we have distance within that we can check, and we can also check whether the boundaries are touching each other with the objects or not. So these are different spatial sequence that are out there that we can use. And some of the functions are like geometric management is ST, and ST is spatial transform, and geom from text is one function, make line as a GeoJSON, then calculating the area, distance, length, then checking whether one thing is within, like whether it is intersecting, whether it is disjoint, whether it touches. So those kind of things, or some other clustering mechanism like cluster DB scan, which is a famous clustering technique that we can use. So this is how we can run SQL on top of spatial data. Some of the common terminologies that I have been working with is CRS, which is a way for which we represent spatial data uh, flattened on a 2D surface. Then we have GCS, which is geographic coordinate system, like it can be lat long, analysis that we do. Georeferencing is another term which is to align raster or vector data to a specific coordinate system. So let's say, for example, if we have raster data in a different coordinate system and vector data in a different coordinate system, because they are coming from two different sources, we have to make them align to the same reference system so that we can point out, or we can, when we say that, okay, this point has these attributes, those are at the actual point which are represented in both the systems. Then we have geocoding, which is a process of converting the street addresses to or other locations into set of geographic coordinates. Uh, then we have resampling, which is nothing but changing the resolution of the raster data. We have reprojection. So reprojection is something that, let's say, if we have two files, two data coming from two different sources. One is, let's say, uh, weather data coming from one agency, and we have weather data coming from another agency. Both of them, if they don't use the correct grid, uh, or let's say uh, they don't use the same set of map projections, then it will be harder for us to exactly pinpoint the attributes or overlay them over each other. So there are concepts like reprojection and regridding, which helps us in making two system behave on the same base. And then we have concept of vectorization, which converts a raster feature to a vector representation. We have a concept of clipping, which is nothing but extracting certain subset of a spatial data that falls within a specified spatial boundary, or we can say point of interest or point area of interest. Then we have B box, which is bounding box, which is an area that defines the outer boundaries of an element. So let's say if we have a water body, a river body going from one place to another place, but it has some tributaries as well. So to this bounding box defines the whole area where which can be completely in which can completely engulf that particular object, or the element, in this case the river's path. Then we have concept of padding, AOI and POI I have spoken multiple times, which is area of interest and point of interest. So these are some terms. Then we have the concept of can be like, because this is also a data, simply let's say GeoParquet or Parquet file system. So can we make a medallion setup with this? Yes, which is pretty much possible. We can have raw raster files present in, let's say, from coming from source in a three location. Then we do some conversion, like we start we con load that source data into bronze layer in the chosen formats. For example, for raster we can use geotiff or cloud optimized geotiffs like cog. For vector we can go ahead with GeoJSON or GeoParquet to store those data, and we can say that whether it will be an append only system, or it will have a version system. So that way we can create a bronze layer. Then we can represent these data in a format which is more suitable for computation, like WKB or GeoArrow. Then we apply some computations on top of it, like tessellation, like creating bounding boxes, mapping AOI with the other things, and then we create indexes on top of it, like we can use BNG index or we can use S3 indexing. And once we have these things done, computations done, we can create a gold layer, which is the layer that will be served to the users through, let's say, notebooks, or from expose as a database for others to consume. So that's the medallion architecture that we can follow with geospatial data. The other interesting thing that is happening is GenAI with spatial data. So, for example, let's say if you have worked, let's say if there's a utility company, it has transmission lines going from one city to another city, and it wants to see if in between there is any scope where some other object is touching their live wires. For example, let's say large trees are touching there, or let's say if there is a large building which is nearby. So what is the area that it should cover in terms of fire, or let's say vegetation data, that we want to know how many trees are in a close range which can grow and touch the wire, causing a fire. So those kind of things. So we have a concept of geotagging, where or simply say tagging. What we do is we take the raster data, we find out the places like which is tree, bus, or other objects that is being tagged. So as of now, that generally there are ecologists who do these things, but now we with GenAI we can say we combine LLM, which is large language models, with LVM, which is large visual models. For example, Facebook SAM, which is a model for visual identifying objects in a image. So what we can do is we can pass both combine the LLM and LVM power, saying that okay, we provide a raster data to a system, and then we say give me uh, spans which have trees touching wire. So that way, the LLM will understand what we are asking. It will convert that into LVM prompt, and LVM will look at that particular image and find out or tag. Create a vectors out of that, and then we can use any spatial framework to build on top of it any product that we want. So that's how GenAI can be used with spatial data. Some common libraries to work with spatial data we have already discussed, like Sapli, GeoPanda, GDAL, Raster.io, Rio Xarray, and Apache Sedona. Apache Sedona is very versatile. It is distributed. It works on top of Spark. Then we have some frameworks or toolbox that can be used with geospatial data. One is Mosaic, one is Kato, Sedona Snow, which is for Snowflake, Sedona Spark, which is for Spark. Then we have ISRI, which builds on top of ArcGIS platform, and Raster Frames, which is another framework which to use to work with raster data. So this was it. This was an introductory what you call video on geospatial analysis. In next video, I will detail about some of the frameworks or the platforms that we can use to work with geospatial data. Thank you.